Welcome to Solideo Gloria Physical Chemistry. So we are going to talk about today quantum theory. And firstly, we'll introduce some historical avenue of classical mechanics that fails, so that we had to introduce quantum idea. Then we'll talk about quantum postulate. There are 6 postulates, basic ones, and then we'll derive the Schrödinger equation. And this basically lay out the kind of fundamentals of quantum mechanics that is maybe useful in chemistry. So let's begin. As I said, I'm not going to go really details of classical mechanics that fail to explain certain experimental findings at the end of 19th century such, but I'm going to just list of them. So 19th century scientists, they could not explain some experimental findings or experimental phenomena with their classical mechanics. So we call those challenges to the classical mechanics. And then those are the black body radiation. Let me have a pen. Black body radiation, then photoelectric effect, and hydrogen atom spectrum, atomic spectrum of hydrogen, then atomic structure. These 4 things, or maybe some others, but these 4 things could not be explained by classical mechanics. So people or scientists concentrate how to explain these within their understanding of laws of physics they have, but couldn't. So they evolved a new idea of quantum that is introduced to lay out the basics of foundations of quantum mechanics. So new idea of quantum introduced to establish the physics. So as I said, I'm not going to detail or any of these historical explanation, but I'm going to just talk about a little bit of black body radiation, more in a little bit more detail how it is derived as such. So that will be okay. So black body radiation is such a thing. There is no really ideal black body. Black body can emit and absorb all frequencies of spectrum, electromagnetic radiation. But black body, we could the cavity inside of the sphere could be ideal black body, or close to the close to the ideal black body. So inside of the cavity, we can consider that as a black body, and we have a pinhole here, so that outside of the black body or the world can interact with the black body. Black body is the cavity. Then the round shape or spherical shape kind of helps it to be equilibrated with surroundings. So basically there's a sphere which has cavity inside and a pinhole to interact with outside the world. And then this whole black body is equilibrated at certain temperature. Okay, there is a pinhole. Then through the pinhole and black body radiate or absorb from outside all kinds of radiation, all frequencies of radiation. And then as a function of frequency, we can obtain the intensity of that radiation. And note that experiment was done, in this case 1500, 1700 and 2000 K. So depending on the temperature, but temperature is fixed, equilibrated heat bath or reservoir. Okay, so at certain temperature, the intensity which is radiated by this black body is recorded in a way that, let me up. So certain frequency, half times 10 to the 14th, 1 times 10 to the 14th, like that. This intensity is, let's pick up the 2000 K. So 2000 K temperature fixed, so it increases as the intensity increases as frequency increases. So as a function of frequency, the intensity of the radiation from the black body is recorded. That's an experimental fact or experimental finding. So it really goes well with classical explanation or Ley-Lijang's law, or classical electrodynamic theory. Ley-Lijang's law also explain that, which is the intensity as a function of nu square. So the intensity is proportional to nu square, so which is really close in such a way that if we just do something like, but not this one, if we do something like, nu like that, nu square curve, it does explain low frequency range, meaning is that low frequency is red or yellow, like that. But when frequencies increases, when the time reaches this frequency and beyond, it reaches the summit or highest point and fall down. So this region is ultraviolet, over the violet, so we call this region is ultraviolet. So in this ultraviolet region, it falls down. So we call this phenomena ultraviolet catastrophe. It falls down. So not only 2000 K, 1700 K, and 1500 K, all temperatures, it initially at low frequency increases as a function of nu square, frequency square, but reaches as the highest point and falls down, ultraviolet catastrophe. So in classical electrodynamic theory, it did not give kind of explanation about this ultraviolet catastrophe. It does not really predict the behavior of intensity as a function of frequency. So that's what the challenge was to the classical mechanics. And that was resolved 1900. October 19th of 1900, Max Planck, a German physicist, and in order to explain the black body radiation or the intensity of the radiation as a function of frequency, he could do it if the energy is, as a conclusion, quantized. So classically, the picture of energy is continuous. Meaning is, when we consider the black body has many oscillator, or atom is vibrating, or molecule also vibrating from its equilibrium position. So that construct, all atoms or molecules construct the black body, vibrate, and it radiates certain frequencies. So this, we call it oscillator or vibrator. Oscillator can have all energies, whatever energies you would like, you could, all energy. So energy is continuous quantity in classical view. That we say classically, all energies, all frequencies are possible. All energy is possible for the oscillator. But Planck's idea or Max's idea is that this oscillator can have only energy as a multiple of something. That something is proportional to the frequency. The proportionality coefficient or constant is h. So the energy is a multiple of h nu or 0. 1 multiple of h nu, 2 multiple of h nu, 3 multiple of h nu, like that, or 4 multiple of h nu, 5 multiples of h nu. So according to Max Planck, what is suggested October 19, 1900 is that the energy distribution of energy of this electromagnetic radiation from the black body is that the energy is quantized, meaning is that it is discretized, not the continuous one, but discretized, chunk by chunk. That chunk, we call it later on quantum. So energy is quantized, quantization of energy. That will explain black body radiation or the behavior of intensity as a function of frequency. Let's go on. So what happened is that Planck suggested that there is a chunk of energy or some unit of energy which is the basis for the multiple. So 1 multiple or 2 multiple or 3 multiple of epsilon h nu. That's Marx suggested. And this h is the proportionality constant. We call it Planck constant, which is 6.6262 times 10 to the 34th joule second. It has the unit. And also, we need to incorporate Boltzmann's idea or Boltzmann's distribution or Boltzmann's statistics in such a way that, okay, so here, let's look at energy levels here like that. So this is epsilon 0, 1, 2. So energy goes higher, increases. Then number of molecules or oscillators in this case, N0. Then this is N1. So N1 oscillators at energy level 1 with epsilon 1, energy epsilon 1, and 2 for the second level, and 3 for the third level, like that. But this number of oscillators or number of occupants of the energy level is proportional to this Boltzmann factor, which is energy factor e to the negative energy over kT, okay, multiple of k. So this is the Boltzmann formula or the population incorporated by the Boltzmann factor. We call this e to the minus epsilon over kT is the Boltzmann factor. Okay, so this is the Boltzmann statistics or Boltzmann formula. So we incorporate this together. Together will derive Planck's explanation or distribution curve, energy, quantum energy, or black body radiation energy distribution. Okay, so at the energy equal 0, epsilon 0, okay, then epsilon I, 0 is the bottom, and then first level epsilon 1, second level epsilon 2, which is I times h nu. So epsilon I is I times h nu. Okay, so we have a picture just like that. 0, 1, 2, 3. This is the kind of picture we have. So And then the first level has an energy epsilon 1, which is h nu. Epsilon 2, 2h nu. Epsilon 3, 3h nu. And then n1 is the number of oscillator at the energy level 1, which is n0, the number of oscillators which occupies zeroth level, the bottom, times the Boltzmann factor, e to the h nu minus h nu of n2, which is n0 times e to the 2h nu, because the energy is 2h nu over kt. And 3 is n0 e to the 3 minus 3h nu, because the energy of this level is 3h nu. Okay, so this is it. Then total number of oscillator is the sum of n0 plus n1 plus n2 plus n3, etc. So this is actually n0 is common, and then the first term is 1, and second term is this, and third term is this, meaning is that this is a geometric series with the first term 1, and the ratio to the previous term is e to the minus h nu over kt. So basically this is a kind of sigma summation formula, and sum is given here as a geometric series. And total energy, this is the total number of oscillator. Total energy is that this one. The bottom is energy 0, 1, 2, 3. So the energy contributed from the zeroth level is 0 times n0. First level, h nu, the energy, times n1. Second level, 2h nu times n2. Third level, 3h nu times n3, so on. So this is the summation formula. N0 is the common, or here, and IH nu is the energy, and then this is the factor. And this one is a little bit different from geometric series, but the summation formula is here. So which is H nu it's a common, can go outside of this summation. So I times E the something I. Okay, so Y is here is E to the minus H nu over K. So I times Y to the I's power. Okay, so this is the summation rule. This is a geometric summation rule. Then, so we have total number of oscillator, total energy. So if we divide the total energy with the total number of oscillator, we'll have a average energy. Average energy, epsilon bar, is E over N. Then put this and that over here as a ratio. Then we'll incorporate these two from this summation formula. And then we'll end up with this. So this is the average energy of oscillators that construct the black body. Okay, look at this formula, and usually if h nu, which is very small compared to kt, in that case we can expand it to the x, okay, which is 1 plus x plus factorial square, something like that. Yes, but anyhow, yeah. So so we drop 1 to third term over. We'll have just simple form like that. And if we have this term over here, what we have here is 1 closes out, h nu closes out, and then bar or epsilon average energy or per oscillator is kt. So this is the equipartition theorem. Why this equipartition theorem is that equipartition theorem tells you that at a certain temperature, each degrees of freedom that takes the form of something square has contribution to the energy, which is half kT. Here you have a potential term and kinetic term. So kinetic energy is in one dimension is 1/2 times mass m v that direction, for example x, v square, vx square. So it's one square term. Potential energy in this case, if this is oscillator harmonic term by expression, then 1/2 of k x square. So two square terms here. So 2 times 1/2 each. So shown by is kT. That's why we call it equipartition theorem. So that's it. So we just evaluate this, and then we need another idea from standing wave. Standing wave. So standing wave here, the length of this fixed, or length of this or string is fixed to the point. Okay, so this point is L. This distance is L. Oh, this distance is L. That is fixed. Then, if the wavelength, if there is a kind of wave, then the wavelength is usually from here to the same point. That's a wave, one wave. This distance is wavelength. So that wavelength, half of the wavelength is half of the wavelength. So a whole length or distance is a multiple of the half wave length, half of the wavelength of the wave. If that the whole length is the multiple of it, then we call it standing wave. So this guy just what is standing wave is. So standing waves are, the wavelength is the whole distance of those two fixed points, initial at the end. So that distance is a multiple of half wavelength. So basically the formula is n times half wavelength is L. And lambda, which is the wavelength, is given as 2L over n. N is 2L over lambda. And if we make a derivative of it both sides, or dn d lambda, something like that, and dn equals then derivative of lambda, which is minus 2L over lambda square. Okay, so this is the relationship. This is one dimension. In 3 dimension, when you incorporate the solid angle, then which is dn equal minus 4 pi v over lambda cos q, cos, then lambda. Okay. Now you have the relationship something like wavelength times frequency is speed of the nu lambda equals c. C is the kind of speed of, in this case, because we are dealing with electromagnetic wave, c is a universal constant, speed of light, speed of electromagnetic. So nu is c over lambda. Then you replace this lambda with nu, okay? Incorporating d nu equals minus c over lambda square d lambda, like that. That's why you have lambda force here. You have lambda force here, so that you replace this lambda with nu, which you end up with dn is 4 pi d over c cube nu square d nu. This is the relation. Okay, so now you have this, and then what I mean is that you have dn equals 4 pi d c cube nu cube d nu and epsilon bar. There are two. So you put this together to obtain number of oscillators per unit volume. Okay, number of oscillators unit volume is this one. Then the intensity as a function of nu is coming from energy times the number of oscillator. So energy times the number of oscillator per frequency. So this together, meaning is that epsilon bar times dn, which means that per wavelength or per frequency window, okay, certain frequency window, nu, you have dn many oscillator and times average energy, that is the energy per d nu window, frequency window. You have two here because the standing wave goes forward and backward. And then per unit volume. So this is the formula that gives you intensity as a function of nu. So you put this together with 2 and divide by b. b is divided, so it does not show up here. So 2 times 4 pi, 8 pi, then h nu cube, square and 1, so cube, then c square, c cube, I'm sorry, and d nu, then just this denominator. So that's basically this. This is the formula. And then if you plot this formula as a function of nu at a given temperature factors here, the given temperature at 4000 K, 5000 K, 6000 K, and it fits. Well, this solid line is experimental, and it fits the experiment. And actually, Planck fits the experimental data with this formula and derive this constant, Planck constant. And this dot line is what? Rayleigh-Jean's prediction. Then it now explain the ultraviolet. So Planck distribution or photon energy distribution did explain the classical finding about blackbody radiation. This has very useful application in terms of real life. So people find the surface temperature of the sun, because we could not go there to temperature, but people observe the radiation from the sun, then find out from the distribution of the radiation energy, find out the temperature just by fitting. But actually this is the solar radiation intensity. By fitting this to the Max Planck formula. So this is the Max Planck formula in terms of lambda instead of nu. Then we make a derivative of this with respect to lambda, and then there is a maximum. So that maximum we could determine just like that, and that maximum times t is this number. And then that maximum lambda max is from here, from the observation, which is about 500 nanometer. Okay, nanometer. So lambda max times t is this number, that is this. then you divide by lambda max, this number, then you will obtain 5800 K, just about 6000 K. That's how we know the temperature, surface temperature of the sun. So that's one kind of explanation for the body radiation, or result of the Planck's derivation, Planck formula for the black body. Okay, so we just have taken looked at the black body radiation. Then we'll switch to a bit of different topic, which we talked about this a little bit before. So c is the speed of light. Is the speed of light. C is the speed of light. Then, which is nu times frequency times lambda is wavelength. This is the universal constant. So we are going to talk about the nature of light. So what is light? Light is particle, or light is electromagnetic radiation. Classically, people knew both. Newtonian optics says that Newton optics explained that light goes straight path, then it deflected with a certain angle, the same angle as inflection in and out, the same angle. So that kind of Newton optics demonstrated or explained that light behaves like a particle. And then, but classically we know that light is electromagnetic radiation because it interfere and diffract. Those are classical items in electromagnetic theory. So people could say that light is wave or light is particle. But actually light is both. It's wave, at the same time it behaves also as a particle. So we call that as a wave particle duality. So that is the phenomena we describe the light as wave or particle, wave particle duality. So this is not really what light is. This is just the way we express or explain or talk about and understand what light is. The light is wave. At the same time, we can explain the phenomena of light as wave or particle. So this kind of a dual wave and light, wave and particle nature of this we call wave particle duality. It is rather realized or kind of utilized by de Broglie in that way. 1923, Louis de Broglie proposed rather a strange formula for it that way. How strange it is that, this was a kind of very famous formula, e to the E equals mc square, but actually this m is kind of a mass of the lost mass. Okay, E equals mc square, but this m times c is the speed of light, which is actually mass times speed or velocity is momentum. So mc square is pc, but you see this m is kind of not real mass. It's a kind of mass lost in the kind of action. See, he used it. But and also, light does not have a mass. That's a problem in this development. And then energy is h nu. Planck showed that the kind of fundamental or the very unit of energy is h nu. So Pc equals h nu. Now nu is here c over lambda. So this is h nu hc over lambda. Now you see here Pc equals Pc, momentum times speed of light, is lambda h over lambda times c. So what we have is P equal h over lambda, or lambda equals h over p. P is a particle number, anyway, that's a momentum. M times c is the speed of light, or m times c, that's P. Then lambda, which is a kind of wave nature, is coming from particle nature. So wave and particle are the same notation or same concept or same notion of the light phenomena, but we call it a matter or wave, matter wave. So this is the Broglie's matter wave. It's the matter wave. Then that's just the idea. Actually, he just wrote down it on a piece of very small piece of tiny paper. But what happened is that was 1923, de Broglie's matter wave. In 1928, people, meaning is that Davison and Garner, did that experiment. What experiment? And actually, they used nickel crystal. They used nickel crystal and shine with X-ray, and then X-ray is diffracted by the crystal. That's a wave phenomena. So X-ray diffraction pattern is, and then they used the electron ray. Electrons, they kind of shot it with electron, but you see, electron also diffracted X-ray as X-ray diffracted. The same, well, actually, electron is much kind of electrons have much higher impact to the kind of surface, so it has very dense pattern. But anyhow, Davis and Garner could observe wave behavior out of electron. So that really establish or support de Broglie's matter wave idea. So matter wave is real thing. That's what the message. That's the message from Heisenberg experiment. Okay, so people now is able to explain or treat matter as a wave or wave as a matter. But by doing so, there is a kind of, it entails that idea, incorporating those two, meaning is the matter wave, incorporate wave behavior incorporated into particle behavior, or particle behavior incorporated into wave behavior, entails that uncertainty principle. So we call it Heisenberg uncertainty principle. What it is that now we treat the object like wave as a particle, and then we can incorporate the wave function to the behavior of particle. So the wave function can be a state function of the particle. So de Broglie wave for the particle is kind of the particle now can be described by a wave function. Wave and particle are the same thing. Okay, just one thing. So then there are many number of waves could represent a particle. So the Broglie wave for particle is made up of superposition of infinitely large number of waves of the form. This is just one form of wave depending on frequency and the wave number. Wavelength. So wavelength is incorporated into spatial dimension, frequency into time dimension. Okay? Yes. Then we have kappa, which is wave number, reciprocal of wavelengths, and then just this one, either way. So what we have here is that the uncertainty in x or lambda or x, the same thing, and delta x, delta kappa, delta x or delta 1 over lambda, which must be always greater than or equal to 1 over 4 pi. Also, for the time domain, delta t times delta nu must be equal or greater than 1 over 4 pi. So when we do, well, now, for example, this k and kappa and x and t and nu are complementary variables. We call those complementary. So what we have here is that 1 over lambda could be px over h. Remember that lambda equals h over p. Okay? This, which means that delta x times delta px, h goes here. Now h bar is such a thing, h divided by 2 pi. Right? So we have this expression like delta x times delta px is equal or greater than h bar over 2. Likewise, we do the same thing for E delta E is actually nu is E over h, because E equals, remember that, h nu. From there, what we have is delta t times delta E is greater than or equal to h bar over 2. So this is the statement for Heisenberg uncertainty. You cannot determine both delta x or px, momentum and position, but time and energy, not exactly, precisely determine those at the same time. So certain uncertainty, product of those uncertainty must be equal to or greater than h bar over 2. That's uncertainty principle. That's why how, where came from. Where is we express the behavior of particles of wave. This is intended. Okay, now we are at the position to derive Schrödinger equation. Switch Schrödinger equation. The Schrödinger equation, this is the wave equation. So when we incorporate matter wave into the regular wave equation, see, this is that kind of a round scale u round x square, 1 over nu square round scale u round t square. So u x t 1 over v square u square. So just to remember this is just like F equal ma, something like that, just Newton equation. equivalent to that, this is a wave equation. Now, u is a kind of position dependent, kind of amplitude of the wave, position dependent and time dependent. So u is a function of x and t when we are dealing with one-dimensional wave. So that depends on position and time. So that's the amplitude. So u is the amplitude as a function of x and t, but that u is related to x and t in this way. That is the wave equation. So now in order to solve this differential equation, we are going to separate the variable. So u as a function of x and t now is a function of x times function of t. So we just use a kind of sinusoidal function, which is here is cosine omega t, and psi x is only function of only x. So we call this is a wave function. This is that satisfy the wave equation, and also that wave function could be a function of time and function of spatial variable, in this case x. Okay, but sometimes we just call this part only as a wave function in space. Okay, yes. Then we put this u over here and then make this derivation. Then what we have, separate out the cosine omega. So we are ending this x only. Well, actually, this is not that difficult and very simple thing, because this part, when you do the derivative against x twice, omega t, cosine omega t is a constant there. Just to do times constant omega t. Then when you derive this sine omega t twice with respect to time, what you have is that what you get back is that minus omega square cosine omega t. So cosine omega t in both sides cancels. Then you have omega square. Okay, this side minus, but you did the left hand side. Now you have plus, which is over omega square over nu square. This is the resulting equation from this, incorporating this into the differential equation. Okay, we have here now omega is 2 pi nu. That's the definition. Okay? Then we utilize this u lambda equal, this is free, very similar. This is free speed. Okay? Now then we use omega square is 4 pi square. Okay, 4 pi square instead pi square this is free. This is free, not no. So so v square is nu square lambda square. So lambda square is there, but nu square here, this nu square cancels. So only this nu square is gone. Then what left is 4 pi square over lambda square. This differential equation. So we are now here. Now we put energy. Energy is the kinetic energy plus potential energy. Potential energy is a function of x. So, well, at this point we have only a function of x only. So energy equal p square of 2m, which is actually 1 over 2 m v square, which is mv is p, so 2m over m square square 2m. So this is kinetic energy, measure energy. Okay, so this is the kind of energy formula, and now we are incorporating matter wave. Lambda equals h over p, and p you obtain here as that 2m e minus b of square root, okay? Square root of them. Okay, so p is here. So lambda is this one. So instead of lambda square, we have put here square of this reciprocal. So that reciprocal is e minus 2m times e minus b over h square. Okay? But what was there is 4 pi square. So 4 pi square over h square is that h bar square. What you have here. So this is the wave. This is the Schrödinger equation. But there is no time dependency. So we call this one time independent Schrödinger equation. So in a neat or beautiful format like that, just to rearrange this so that we have energy in this side. So which is minus h bar square over 2m e square psi d x square plus vx psi x equals e times psi x. Okay, so this is the time independent Schrödinger equation. Now I expect you expect by yourself should be able to derive Schrödinger equation from the wave equation, just to utilize that photon energy and matter wave. So this is not just coming from somewhere from there. We can derive it from very fundamental equation and the wave and the energy. This is total energy is kinetic energy times plus total energy. That's the idea. So once we have wave equation, which we call Schrödinger equation for the matter, in this case particle, we can explain or show the behavior of the particle in terms of wave function. That's very fundamental. Actually, quantum mechanics is very mechanical. It's very straightforward explanation, description for the now we are at the position to deal with quantum. As I told you, we have something like 6 or 7, maybe more. But anyhow, the elementary level we just follow. That's basically this. So 5 postulate here, maybe 6 postulate here. Then this is very fundamental. Postulate is something that which is true, or we assume that is true. Then it can explain whatever it is there in that domain. So postulate is something that it is true. Then it supports the conclusion driven by this structure of the quantum postulate is that we assume or we know what is true for the quantum mechanics. Then based on this, quantum mechanics can explain without any discrepancy the whole phenomena that is dealt by first postulate, which is that states that there is a state function. State of a matter or particle is described by a wave function, which is the solution of the wave function, wave equation, which is the Schrödinger. So the state of a quantum mechanical system, state is completely specified or described by a function psi x, which was the solution for the differential equation. that depends upon the coordinate of the particle. It's a function of x. All possible information, all information about the system can be derived from psi x. This function psi x, or the wave function, the state function, has the important property is psi star psi. Psi star psi, meaning the psi star x times psi x when it's complex number, or just the psi square, psi absolute value square. Dx is the times dx. Okay. It's the probability that the particle lies in the interval delta x, which means that x plus this interval where the particle, this interval, that's the probability. The probability that particle lies or is in this position, that is this number, the wave function value square. That is so. Let me explain a little bit or develop the idea further. In classical mechanics, we denote the state of a particle in terms of position x and y and z in three dimensions. Px, py, z. So position and momentum. Three position variable, three momentum variable, three dimensions. We call generalized position, generalized momentum. So-called momentum and position together describe the state of the classical body, classical system. We call, well, actually this looks like a six-dimensional vector or six-dimensional point. So we call this is a collection of these points. It's a phase space. So we call this point in the phase space. So classical, the state in classical mechanics is described or denoted by the point in the phase space. So in order to state the state, in order to say or describe or tell something about the system is to say that it is in that point of the phase space. Meaning is that you just tell the position and momentum and position, and basically state, tell what state it is. That's classical mechanics. But in quantum mechanics, instead of the position and momentum, you just say what is the state function. This. So in quantum mechanics, the state is denoted or explained or described by which is the solution of the Schrödinger. That's why the Schrödinger equation is very important. Key, it is just to drive that. Okay, so here now, let me explain a little bit about the base wave function. So wave function is actually probability amplitude. The probability amplitude. Why? Actually, this is the probability. Psi star psi dx when it is complex. Or if that's real, just to have psi square. Okay? Dx is the probability. When in 3 dimension, first have the dimensional function, then put the volume element to obtain the probability where you find your. So psi itself is a probability amplitude. Probability is psi star psi dx, or psi star psi dx dy dz. And as I just said, these are the probability. So all probability summation, sum of all probability 1. And this condition, or treatment in all space, so probability itself is 1. That condition we call normalization. Is normal. Because if there is a particle, to find a particle in all space is 1. Space. Now, then we have to describe how this wave function behaves. And it could be well behaved. Well behavior, meaning is that it can be a wave function of a particle, or it can describe system well. That's well behavior. The psi, the wave function, and its derivative must be continuous. That's first condition of well behavior. And it has single valued. Also, because it's a probability, could be there with the probability of something. Let's say 0.2, 20%. But you cannot say that it can be there 20% and 25%. That doesn't make sense. So it must be single valued. And also it is a probability could be finite. Maximum is 1. And also it has to be square integrable, in a way that you have to do this. So that's a square integrable. Square integrable. So these are 4 conditions for the well-behaved wave function. It has to be continuous itself and its derivative. And it's single valued, finite, and square integrable. Okay, so there are some examples. This is well behaved. It's a single valued and continuous and finite and square integrable. This is not. Why? It is at this point it has 3 value. That doesn't make sense. Okay. Also, 2 count or 3 count. It's not continuous at this point. It's continuous. Also, it has 2 values. This wave function cannot be, this function cannot be a wave function. Also, it goes to infinity, so it cannot be a wave function. Also, it cannot be integrated, square and integrated. So, know now what is well behaved. This is the condition to be a wave. This is what behave. And second quantum postulate 2. To every observable in classical mechanics, there correspond a linear Hermitian operator in quantum mechanics. So what we are doing here, in classical mechanics, the variables are x and y and z, position, and px, py, pz, momenta. Those are rather fundamental variables. These could be observed. So we call those variables that are observable. In classical mechanics, we describe the system or physical value, physical quantity in terms of x, y, z, and px, py, z. But in quantum mechanics, we have a linear Hermitian operator that correspond to this observable. So x, y, z, there are operators x, y, z. This caret rotate. It's a notation for the operator. So when you see this caret, it is operator. Okay? There are caret, this is operator. A is an operator. And usually the context tells you there's an operator, so usually we do not put, at the beginning we do, but later on we would not do this caret the operator. There are two things, two reasons maybe. One thing is that it's difficult to put the overhead, this caret, while we are typing. Secondly, the context, your note could be simple by that. And also in context, it tells you that we could safely discussion. Anyhow, if we put caret over some variable that is an operator, okay. So position, we just use x and y and z. Actually, that's a multiplication by the coordinate. That's an operator. And then for px, py, pz, that's derivative operator times minus ih bar. Ih bar times minus ih bar. This is the operator that yields you whatever in classical mechanics corresponding to px, py. Okay, what is linear operator? Linearity of an operator is that, for example, you have a function c1 times f1 plus c2 times f2. This is a linear combination of f1 and f2. We call it linear combination. So when an operator operates to linear combination of two functions, it is the same as the operator function, and make a linear combination. The same way. It's the same way. So A operated on to C1 F1 plus C2 F2, which is C1 A operate to F1 plus C2 A operate to. This A is linear operator. Hermitian operator. You remember this one. You just put this in your mind. What it is that this is regular or normal formula you see many times in quantum mechanics. So integral f star is a complex A operator G dx. Now what you have is that you just move this here with a star. Now you put star to your operator. Okay? And then switch this one into this the other side of the. So this two, this and that are the same. That's what Hermitian property is. So, and then this operator is the Hermitian operator. This the operator behaves just like exactly like this. It's the Hermitian operator. You just remember this form by itself. So to every observable in classical mechanics, there correspond all and every observable in classical mechanics. There corresponds a linear Hermitian operator. That's quantum postulate. Okay. There is an operator relationship like that. An operator A operates to a function, phi x in this case. Then it is phi x, right? Nothing changed, but just multiply with a number. Okay, so this kind of, or this format, we call it eigenvalue equation. Now, this A caret is an eigen operator. I'm sorry, there is no such a thing, such a word here, but this is an eigen operator. Then this A value is an eigenvalue. And this function is the eigenfunction. So this is the eigenvalue equation. Well, actually, the Schrödinger equation is an eigenvalue equation. because you see, you look at you remember this is the Schrödinger equation. So minus h bar square over 2m d square over dx square, let it outside here, plus vx, let it outside here, then just like this. Then this is the kinetic energy plus potential energy, then that's total energy. So these are just well, some function of x is just a time multiplying by that function to the operand or whatever being operated. Then this is just even the differential operator. And then operator plus operator is an operator. We call that as H operator. And then that is the name of that operator is Hamiltonian. Simple word, that's a total energy. So Schrödinger equation itself is that operator times a function, or operator operated the function is an energy which is number times the function. So this is just a form of eigenvalue equation. So that's why we use eigenvalue equation, eigenvalue and eigenfunction. So wave function that fulfills Schrödinger equation is an eigenfunction. So Hamiltonian. Linear operator, I just explained that previously, but I'll tell you here that differential operator, integral operator are linear operator. And there are many, there are fundamental operators, observables. So in classical mechanics, switch should be. And classical mechanics, there are observables. Quantum mechanics, there are operator corresponding to the position x in one dimension, r in three dimensions. Operator x caret r caret. That's the operation itself is the multiplication by x, multiplication by r in three dimensions. Momentum, that's position. That's about what? That's about the position and momentum. Px operator. But real operation is the make a derivative and multiply by minus IH. This is the operator. In three dimension, now IH bar is a multiplication factor, but derivative in all direction x, y, and z, vector quantity. And kinetic energy is that 1 over 2m times px or p square, right? So now you do in such a way that minus IH bar times minus IH bar, which is minus plus I square H bar square. I square is minus H bar square over 2m. Then you derive twice. That's one dimension. Three dimension, you do this. Then this is the Laplacian operator. The Laplacian operator, you have del square. So minus H bar square of 2m, del square is potential energy operator. Potential energy operator as potential energy is a function of position. You just give position, function of position. Three dimension. Total energy operator, we just saw H bar, is that potential energy plus kinetic energy. So kinetic energy operator, 3D, potential energy operator. Kinetic energy plus potential. That's total energy, that's Hamilton. So we use, most in 3D, use this. Actually, that's a kind of Hamiltonian operator for Schrödinger equation. Then, depending on what quantity physical observer we are dealing with, combination of these operators. And Hermitian property is important because observable is a real quantity. It's not complex number, real number. So you must obtain real number. Hermitian operator gives you the real. That's the relation. See, this is the, well, actually, you switch this over here. I'm sorry. Switch, well, actually, it's rather difficult to write down. This is actually what it is the psi, then star. This one. This one, well, A psi equals what? A star psi star psi. Okay, this one is this, right? Okay, then A integral see? Then now these are, let me switch the to go this way. Then, well, this is just the same number. A and same. A star the same. And which means that A is real. Some number is equal to its conjugate, meaning is that it does imaginary real part there. This is the kind of a conclusion for the Hermitian behavior or Hermitian property. Now, quantum postulate 3. Okay, it states that in any measurement of the observable associated with the operator A, the only value that will ever be observed are the eigenvalue, which satisfies the eigenvalue equation. Well, if there's an eigenvalue equation, if you kind of operate to that eigenfunction, you always get the eigenvalue. And just well, given the state is psi n, then can observe only the number an. That's what 3. Quantum postulate 4. But what if psi is not an eigenfunction of the operator? If a system is in a state described by a normalized wave function psi, not necessarily an eigenfunction, then the average value of the observable corresponding to A is this one. Average value. So whatever inside of this angle bracket, or that is average of the average is all space integrated of this quantity, which is actually psi a psi times psi star integrated, because this has a relationship something like this. This is what looks like is I think that this one, if there's psi n, if psi x is psi n, there is eigenvalue relationship is there. So psi a acting on psi n will gives you eigenvalues an, meaning is this relation. And then the expectation or average value is this. then A psi n, A operator psi n is A n psi n, this. Then A n is a number, then this. This is as something like normalized, and 1, which is 1. Yeah. Okay, so basically this is the idea for the quantum postulate 3. But this one is something like, so you operate this, but you don't know what it is. So something like, instead, what you have here is the psi, psi, and some quantity, maybe alpha, which means that alpha times its probability and some the all space. Okay, so probability times some quantity, meaning is that that's average. Probability times quantity summed, that gives you an average. That's expected. Okay, so that's the A. Now you can do A square. A square is that you operate A twice. But you see, this is an eigenfunction. So once n, twice an square. This one is an square. And variance, you remember the variance, which is the quantity A. I'm sorry, say different symbol. Say y. Yes. Square is variance. Square root is what? Is your standard deviation. So there is a formula just like this. Yes. So variance square was the standard deviation square. Variance is a square average minus a average square. So this is 0 in this case. Meaning is that there is no variance, no deviation when you have eigenfunction. This is the case, general case. Don't have an eigenfunction, but any function, then you will obtain that physical quantity corresponding to the observable in classical mechanics from the expectation. Okay, quantum postulate 5, the wave function or state function of a system. This is, up to now, we just dealt with time-independent wave function. Then the question is that how it evolves in time. Time is very important too. So the wave function or state function of a system evolves in time. That evolves in time according to time-dependent Schrödinger equation. We have been dealing with only time-independent Schrödinger. Now it's time to look at how it behaves in time. It's done by here. Just to know this form. So there is no split dependency of time h, which is our Hamilton. Then time dependent wave function is time independent wave function times time. We used it cosine omega. Then we put this and separate out the time independent Schrödinger equation and time part of time dependent Schrödinger equation. Then we obtain this. And this one, exponential of complex exponential form of energy. And then time dependent independent part plus time part will give you time dependent wave function. Then here is time independent apart from this. This is the time propagator. But energy is conserved, means the energy is the same. It's just and then we are going to, well, this we'll just make everything together. Usually we just dealt with quantum postulate 5 and then do this one later on, but we'll just do many particle here too. So another quantum postulate 6, quantum postulate 6 is that all electron, because electron is the most important or key factor in our quantum mechanics in chemistry, all electron wave function must be antisymmetric to the interchange of any two electrons. You remember the Pauli principle, Pauli exclusion. No two electrons can have the same set of quantum. So the wave function is indistinguishable of indistinguishable particle. Meaning is that you have two electrons which you cannot tell one from the other. They are indistinguishable. So indistinguishable particle, for the system of indistinguishable particle, so you have two particle wave functions, particle number 1, particle number 2. Then if you switch these two, meaning is that psi12 and psi21, and psi itself, psi12 is a probability amplitude. Psi21 is also a probability amplitude of electron 1 and electron 2. Probability, even if you switched its position, you cannot tell. There is no difference, indistinguishable. So probability must be the same. So psi12 square must be equal to psi21 square, which means that to do either psi21 is equal to plus minus psi12. So when psi12 equals to psi21, then in the plus part, which is symmetric. When psi21 equals minus psi12, then it's antisymmetric. Okay, so antisymmetry is minus, symmetry is plus. Okay, in this formula. So if this thing is symmetric, we call it boson, or the other words, does fulfill, or it does behave as a Bose-Einstein statistics. If that's antisymmetric, that's fermion or Fermi-Dirac statistics. It follows Fermi-Dirac statistics. So, and then what is fermion, which has integral, half integral spin? What is boson? Boson does have integral spin. Well, spin quantum number, we are going to do it later. 1/2 for the electron. The electron must have antisymmetric wave function. Boson, there are other bosons, which has integral spin 1. It's integer. Those are bosons. Those behave as a symmetric with a symmetric wave. All electrons has 1/2 spin quantum number, so must be antisymmetric to the exchange of any two. That's quantum 6. There are now we have done quantum postulate. There are some theorems about Hermitian operator, which are really useful to further develop quantum mechanics. We are going to do a couple of things. So theorem. First theorem we are going to look at is that eigenfunctions of Hermitian operator with different associated eigenvalue are orthogonal. So if eigenvalues are different, then they are orthogonal. Okay. So this is an eigenvalue equation. Ooh. This is enough. This is an eigenvalue equation. And for the eigenvalue an, eigenfunction psi m. Eigenvalue am, eigenfunction psi m. Okay? Two eigenvalue equations. Now, what we are going to do is the cross product of psi m star and a psi n. A psi n is an psi n. So an is a number in front of the integral. So integral psi m star psi n. We are going to do this. We just did this one. Then we are going to do the other way. So a star psi m psi n. You see, this is the Hermitian property. Those two must be the same. Okay, that's 0. Okay. This is the Hermitian. Each other must be the same. So same thing minus same thing is 0. But you do the calculation or operation just like that. So from first integral you got an, second integral you got am star, and then that's 0. Okay, you have different eigenvalue. First, there's Hermitian, from Hermitian, those are real numbers, and those are different. Meaning is that this everything in the parenthesis is not 0. Meaning is that this must be. So for eigenfunctions of different eigenvalues, the integral is 0. Meaning is that this integral is 0, which is orthogonal. So n and m are not the same, then that's 0, orthogonal. If they are same, then this is 0, that is not. That is not, meaning is that that's normalized. Meaning is that this is real, because this A is a Hermitian. Okay? It says that eigenfunctions of Hermitian operator with different associated eigenvalues are orthogonal. Now, we introduce a kind of new symbol here. Which n equals m 1 and not equal to m 0. So n equal m 1 not equal to m 0. This is the symbol, same symbol, I mean one symbol, delta n, as we call Kronecker. So we can express this integral as delta mn. And degenerate wave eigenfunctions. Okay, well, this case, the eigenfunctions of a Hermitian operator with the same eigenvalue may be transformed into orthogonal functions while remaining eigenfunctions of the operator. What it means that if two eigenfunctions, two wave functions there, and if those have different eigenvalue, then they are orthogonal. But what if two wave functions have the same eigenvalue? What will happen? They are orthogonal or they are normalized? That's the question. But the theorem says that when you have two wave functions have the same eigenvalue, then still you can make them orthogonal while you still have the same eigenvalue. That's what the theorem says. So any linear combination of degenerate eigenfunctions of Hermitian operator is an eigenfunction of. So meaning is that if there are two wave functions have the same eigenvalue, you make a linear combination of it, still the same eigenvalue, but a different function. Then that function could be orthogonal to the previous, the original function. That's what it is. So, firstly, there is a psi 1 and psi 2, but they have the same eigenvalue. So a psi 1 equals a1 psi 1, a psi 2 equals a1 psi 2. Then linear combination of psi 1 and psi 2 is the c1 psi 1 plus c2 psi 2. Use them. This is the linear. Now, you operate the operator, the linear combination. And then this is the linear operator. You do operate first and then find. Then it gives you eigenvalue. Then you reassemble that because the eigenvalue is the same. Then this is psi, phi, this. So eigenvalue equation is the same. Meaning is that linear combination of psi 1 and psi 2 phi is also a function of A. So this is what this statement is linear combination of degenerate eigenfunctions of Hermitian operator is an eigenfunction. And Schmidt orthogonalization procedure is that you are given psi 1 and psi 2. So first choose one, let's say psi 1. Then make a linear combination of psi 1 and psi 2, let's say phi 2. Choose psi 1 as phi 1. Then phi 2, that is orthogonal to phi 1. That's the procedure that gives you the C combination coefficient that gives you orthogonal phi 1 and phi 2. See here. So any two eigenfunctions have the same eigenvalue. Can make a linear combination of two that is orthogonal to one of them. That is Schmidt orthogonalization. Very close. And commuting operator. If a set of eigenfunctions are eigenvalues of two linear operators and B, then the operator commute. Commute means that either if you have two operators A and B, either way, you first operate A and then B, or operate first with B and then A. Okay? So operator must have an order, but you can switch the order. Then it's commutable. We say that those two operators commute. So if two operators commute, it's possible to find a set of functions that are simultaneous eigenfunctions of both. These two are the kind of corollary, same thing, same theorem. If a set of eigenvalues if a set of eigenfunctions are eigenfunctions of two different operators A and B, then operators commute. Or two operators commute, it is possible to find a set of eigenfunctions, that are simultaneous eigenfunctions. So this shows how it works. A phi 1, AI phi 1, B phi 1, BI phi 1. Okay, or A phi I equal AI phi I, B phi I, BI phi I. Phi I are the phi I same. Okay, same phi I. Then AB phi I. Now you operate B first. So A BI phi I. BI is a kind of number. So BI A phi I, BI AI phi I. So you switch this order, then you obtain this. But BI AI BI are the same. Okay, so you subtract BA phi I from AB phi I equals 0. Meaning is this 0. Now we kind of make this AB minus BA phi I equals 0. So this is the kind of null operator. meaning is that AB minus BA equals 0. Especially we call this operator times operator minus operator times operator operator is an operator. We call that as an operator in bracket A, B bracket. We call this commutator. But there, okay, this is the commutator equal 0. Well, I think I'm spending too much time, but but there is something like anti-commutator. Anti-commutator is something like this. That's commutator. In this case, you put minus here. Then plus maybe. That probably might. Then which is a B. Just a kind of. Okay, so let's do it. Okay, uncertainty in simultaneous measurement. Okay, you measure two observers together, A and B, at the same time. Then there is an uncertainty. That's what it says. But actually, Heisenberg, the uncertainty principle is based on this. So you have two operators. Okay, two operators. A and B. Then a commutator relationship. Okay. Commutator is an operator. So you could do this operation. A and B equal 0, commutator equal 0, meaning is that A and B are simultaneous wave function. Okay. If this is 0, A and B are determined with no uncertainty. They are certainly determined. But if not, what happens? If this is 0, they are simultaneous eigenfunction. So in this case, there is no uncertainty. There is no uncertainty in this case. But if not, what happens? So there are two operators, Px and x. Okay? Remember the Px is minus IH bar ddx, Px and x, xxx. Okay. So when you do this operation, then you do xpx operation. See, we switch this, and this one, firstly, you make a derivative x and psi. So make a derivative x is 1, IH bar, psi. Then you leave it alone and make a derivative psi x. So you leave it alone, and in this case, you just operate that. So you subtract this from that, but you still have this one. Subtract that and this one. But this is the commutator, which is IH bar, and this I is multiplying by 1. IH bar. So if you put this one here, what you have here is that IH bar, so-called identity operator, which is 1. If that's the eigenfunction or wave function, then what you have is that minus IH bar. Normalization tells you this is 1 times IH bar. There is a 1/2 there. So 1/2 IH bar. This is just H bar because the minus I absolute value of it is 1. Then this is H bar over 2. So Px Py uncertainty is always greater than or equal to H bar over 2. Just as Heisenberg uncertainty principle told you previously. So now we are going to wrap this up. I think I'm doing about 2 hours now. Sorry about that. We just to finish the whole idea of this time. So there are classical mechanics and quantum mechanics. We are putting this side by side. So in classical mechanics, what we have or about state or say or tell the state, describe the state as a point in phase space. Then we know the evolution time as the trajectory of the phase space. So Q and P, generalized coordinate generalizer form, XYZ, PX, PY. This describes the state of the system as communicated. And then equation of state is F equal ma. Actually, this F equal ma thing is that gradient, negative gradient potential is force, negative gradient, say energy. That's potential energy. So now I would do negative force S X square. See? This is F equal ma. This is the equation of state. But well, let's finish the classical mechanics. So in classical mechanics, dynamical variable is observable. These observables are x, y, z, and x, q, z, or combination of these. That's what classical mechanics does to describe the world. Quantum mechanics, we describe or denote or say the state of the system, state function, which is a wave function. Wave function is the solution of this equation, Schrödinger equation, or that's the wave equation for the matter wave. And then for the dynamical variable, they correspond to linear operator. An observable could be obtained by either eigenvalue or average of it, expectation. So quantum postulate 1, quantum postulate 3, 4 operate here. Second quantum. Yeah. And then these are the operator correspond to this observable. The observable, that's the. Basically, this is what quantum mechanics is against classical mechanics, or based on classical mechanics, we evolved, developed this way. So this is how it works, quantum mechanics. So we have this potential energy, the given system. For particle, well, we'll do these four problems the following lectures. Actually, 1925 or 26, Erwin Schrödinger solved this problem in the journal by that time. That is physics. That very long time ago I read that. But anyhow, so these four problems have different potential energy. Given the potential energy, particularly in a box 0 infinity, rigid rotor is 0, harmonic oscillator half kx square, hydrogen atom minus e square over 4 pi epsilon 0 r. Given the potential energy, which is this one, then you construct the Hamiltonian operator, which is minus h bar square of 2m d square dx square plus vx. That's how about this one is plus this Hamiltonian operator. Meaning is you construct Schrödinger equation So given the potential energy, you construct with the potential energy you construct Hamiltonian operator and then Schrödinger equation. You solve it to obtain psi. When you have psi, you want to obtain dynamical variable or quantity of it, and you assemble it into an operator A. Then you operate that operator to your wave function, obtain eigenvalue. That's an eigenfunction, or otherwise you expectation. So basically, this is how quantum mechanics works. Chemistry. I think this is the end of the lecture. I really grateful, patient. Hope this help you going straight through from the beginning to at least the fundamental in chemistry.